Swayam Prabha. Digital India. Educated India.
Good morning everyone, welcome to week number 4 of our MOOCs course on the topic of principles of mechanical measurement. Over last 3 weeks we have discussed about several initial concepts, like in week number 1 you were introduced to the design of a basic measurement system. We talked exclusively or extensively about different kinds of errors which may get intruded during your measurement and also how to eradicate those errors. Then in the second week we have talked about the mathematical representation of any generalized measurement system and the response of 0th order, 1st order and 2nd order measurement systems against some standard inputs. And now in previous week we have talked about the analog to digital conversion, or I should say the digitalization of measurement systems, because most of the measuring tools that we get nowadays have a digital interface and digital output. So once you have the output or readings from any particular measurement system, then we generally need to go for some kind of data processing, and also several other associated steps like converting the data from one particular kinds of signals to another kind of signals, which is conventionally called the transduction. And also quite often you have to go for some kind of amplification or filtering of the measurement signals. We have to generally convert them, any kind of inputs, whether mechanical or thermal, whatever inputs you are getting, most of cases we convert them to some kind of electrical signals to get an electrical output, which is the most easy to measure. And all this comes under this data processing module. Of course this is an extensive things which can include the most intricate electronics, concepts of electrical engineering. We can also include several computational aspects like the use of microprocessors, the use of several digital conversion techniques, image processing, etc. But still we would like to keep this one short, mostly restricting ourselves to electrical measurements or electrical readouts. This is the week where you are first time going to get idea about some real measurements, because in all the previous week we have discussed, previous 3 weeks in all the previous lectures we have discussed about only basic topics, but this week we are going to talk about measuring certain electrical quantities, converting or amplifying those signals, and so that we can have a background about how we can measure different parameters, different output level parameters, and with that concept we can go forward in the next week, in the subsequent weeks, about real measurement of different parameters. I would like to keep this week a bit short. We had quite extensive discussion in the previous 3 weeks, each of having 3 or 4 lectures, and I would try to finish this particular week in just 2 lectures, so that I can give a bit of relief to all of you. Now if we look about any general kind of measurement process, we can always try some kind of start with some kind of physical quantity, and that physical quantity gives certain input signal which is sensed by your primary sensing element, and then that goes to some kind of variable conversion, if required some kind of variable manipulation. Like just think about something that you already know, as we have not talked about any real instrument so far. So I can give you example only from something that you already know. Just think about one mercury thermometer or something conventionally known as the liquid in glass thermometer. So there we would like to measure the temperature of something. Let us say we want to measure the temperature of a human body. Then we are going to take that thermometer in contact with the body, and then what is the first physical quantity? You want to measure temperature, but what is going to be your input signal? What do you feel? Input signal is not going to be temperature, rather your input signal will be in the form of the temperature difference between the body and the thermometric fluid, initial temperature of the thermometric fluid at least. So let us say if your body is at some temperature T0 and thermometric fluid is initially at some temperature Ti, then assuming T0 to be greater than Ti, then this we are going to get certain amount of heat being transferred from the body to the thermometric fluid, which should be proportional to this temperature difference. That means some amount of heat will be transferred which will be proportional to this temperature difference, and this heat transfer will continue till the temperature of the thermometric fluid increases to attain a thermodynamic equilibrium. What I mean is that this T naught, that is the temperature of the body, will remain same, but the temperature of the thermometric fluid, let us say it is called TTF, which is initially is Ti, that will keep on increasing till this Ti increases to attain this higher value of T naught, and then only the system will be able to attain certain thermodynamic equilibrium or thermal equilibrium with the body. So, at any instant of time, the temperature difference between the body and the thermometric fluid is T naught minus TTF, which is again a function of time, with Ti being the initial temperature, and the amount of heat that is going to get transferred, I should not write a dot, amount of heat being transferred is a function of time, and that is going to be proportional to this temperature difference, and that is going to provide this heat transfer is the one that is going to provide your input signal, or if I write your input signal is going to be this Q dot amount of T or Qt. So, this heat transfer will continue till the temperature of the thermometric fluid attains this T naught. Let us say over a delta T period of time this heat transfer has taken place. So, the total amount of heat transferred to this, if I put a rate notation now, is over this period 0 to delta T, and this is the way the amount of heat is being transferred. So, total amount of heat being sensed by this primary sensing element is Q, leading to a change in its temperature from some initial value of Ti to the final body temperature of T naught. Now, once this primary sensing element has got this, then it will produce or rather it will transduce this input signal to certain form, and that form will depend on the nature of the instrument and also its mathematical characteristic. Like if we again go back to the example of thermometer, then this heat actually is going to get converted to a change in temperature of the thermometric fluid, and then that will get transduced to the change in volume of the thermometric fluid through the capillary column. So, while your actual primary input is this amount of heat Q, this variable will get converted to give some delta V or of the thermometric fluid, or maybe some change in the length delta L of the thermometric fluid in the capillary tube. So, that is a variable conversion stage. This is where the mathematical model comes into play, which relates this temperature difference to this delta L. Certain situations we may have to go for some kind of variable manipulations also, like if the delta S is too small, we may go for certain kind of amplification by changing the diameter of the capillary tube, etc. And finally, we get some amplified signal. And now, this is the role where of the data processing unit that comes into picture. Data processing refers to all these stages, like the transmitting the data. Actually, variable manipulation can also be considered to be a function, one of the functions of data processing. So, the data processing unit is going to first perform some kind of manipulation over the transduced signal, then transmit that to the recording part. If required some further data processing, like if there is some kind of feedback kind of options, then this data processing element will do that feedback or certain other processing on this. Sometimes we may have to go for some kind of integrating or differentiating action on this. So, all this will be done in the data processing, and finally, the data presentation to the observer or sometimes recording. So, all these four, one is this variable manipulation, then 2 is the data transmission, 3 is some further processing, optional processing, and then number 4 data representation and recording. All this comes under the purview of this data processing unit, and we shall be discussing just a few glimpses of each of this with particular focus on the data manipulation part and also the data presentation part. Now, it is possible that the final output, like if I go back here, this data presentation that we are talking about, it is possible that the final data that will be presented to the observer or maybe recorded to some kind of recording device, that generally can be done in 3 possible modes. That is, your measurement system can give output in 3 possible modes. One as a relative displacement, second in a digital form, third I shall be coming shortly. What do you mean by relative displacement? Like the thermometer. Here the initial position of the thermometric fluid may be something like this, then because of the heat being transferred from the body under consideration, there is a change in the column height. So, this much of deflection or displacement has taken place of the thermometric fluid inside the capillary tube, which is proportional to the amount of temperature difference, or in a way that gives you a measure about the temperature. Another example of the same thing, but it is the digital form. Here, instead of getting a deflection like in case of in the first example, now once the thermometric fluid reaches this final position, we have to compare this position, we have to compare this position with the scale. Like here there are two scales shown on this thermometer, one in Celsius, one in Fahrenheit. If we compare this tip of this thermometric fluid with the scale, it is showing something just above the 30 degree Celsius and corresponding reading on the Fahrenheit scale. So, we have to compare that to the corresponding scale to get the magnitude, to get the value. Whereas, in case of digital one, we are directly going to get the value for this. Of course, this particular conversion is done internally, and we are going to get the output not in terms of a displacement of something, rather in terms of numbers or digits. That is what refers to the digital form. Another example, this is a common speedometer that we can have in different kinds of vehicles. Now, what kind of form of output that we are getting here? Initially, when the vehicle is under stationary, this indicator will be in some position like this, that is 0, and as you start the vehicle or keep on moving with this, it will keep on rotating over this, keep on getting deflected over the scale, and its instantaneous position gives you the instantaneous velocity. So, this is a deflection type thing. Whereas, we can also have a digital version of the same. You will find several modern vehicles, modern cars can directly give you the velocity value just like this. So, both the modes are possible, both the modes are used for to get the same kind of measurement, like we have the examples of temperature and velocity measurements here, where we have very common instruments to give both kinds of outputs. But there is a third form of output that is also possible, which is a logical indication or yes no kind of output. Any idea where you have seen this? I am not going to go for any kind of mechanical device, because we are not going to use this one that much, or we do not use this that much apart from some specialized cases, but something you probably have seen, or you definitely have seen in your chemistry laboratory. Have you heard about litmus papers? That is an yes or no kind of thing. Like you know that if we have a blue litmus paper and if we immerse that to certain kind of liquid so that its color turns to red, then that liquid has to be an acid. Similarly, if a red litmus paper turns blue in contact with a certain liquid, then that has to be a base. So, you can think this way: you have a blue litmus paper. If you are dipping this to several liquid samples that you have with you. If it is not changing in its color, then it is not an acid. So, your question is whether the liquid is an acid, your answer is no. However, if it changes its color to red, then that is an acid, answer to the question is yes. Same about base, if you have a red litmus paper, if it turns blue in contact with something, then that is a base, otherwise it is not. So, that is an yes no kind of answer. Of course, when it is not at all giving you any idea what is the nature of this. Like suppose a blue litmus paper is continuing to be blue in contact with certain liquids. So, you know certainly that is not an acid, but that may be a base, that may be some kind of salt solution, that may be certain kind of alcohols or certain other organic fluids, but definitely not an acid. And even when it tells you that it is an acid, means its color changes to red, you do not know the chemical composition of the acid, it just tells that this is an acid, that is all. So, it is giving you a logical indication only yes or no. Now, analog indicators, there are different ways we can get analog output, like we have seen couple of examples in the previous slide, the deflection of the mercury column or thermometric fluid column in a capillary, the deflection of indicator on a dial gauge. But in most of the cases, you will find in most 70-80% instruments, we generally transduce this output signal into some kind of electrical form, maybe voltage or current, and then measure that voltage or current, because measuring electrical signals or electrical quantities are quite easy, like we shall be discussing shortly. Therefore, we shall only be talking briefly about electrical indicators, which gives you this analog output in terms of certain deflection of the scale. So, there are generally 6 different categories of electrical indicators that we can get. Electromagnetic, which refers to the interaction between electric current and a magnetic field. There we can have several subclasses, like we can have a moving magnet type, we can have a moving coil type, or a moving iron type. Then electrodynamic, which talks about interaction between currents only, no magnetic field involved. We can have electrostatic as well, where it is electrostatic interaction. Then thermal, related to the thermal effect of current, that is the Joule heating or I square R loss, which can have direct or indirect action. Then we can have induction in the form of magnetic induction, and finally electronic signal processing in the form of analog or digital. Out of this, this first 3, that is electromagnetic, electrodynamic, electrostatic, and also this induction, these 4 are commonly known as electromechanical meters or electromechanical devices. If the device is used to measure certain voltage, we call them voltmeter. If used to measure current, we call them ammeter, but the operating principle remains the same. Let us just quickly touch upon the electromagnetic meters. For electromagnetic meters, the basic operating principle is based upon the d'Arsonval movement. And what is that? Let us quickly see this YouTube video. In case of a d'Arsonval movement, basically we have interaction between, like in case of any electromagnetic case, we have an interaction between a magnetic field and current. Like we have seeing here, we have a U-shaped permanent magnet, and these are the 2 poles of this. So the north and south pole are placed, and in between you are putting a core. Core means some kind of soft metal core. Generally we have an aluminum frame and magnetic coil. On top of this we have this particular frame, which is housing the pointer, which is going to move over a certain scale to give you the final reading. So the pointer is carried by the spindle and it moves over the scale. The scale is shown somewhere here on this video. You will shortly be seeing the action of the scale also. The coils are wrapped around this particular frame, and there are jewel bearings, or there are supporting something else to support this, and also there are a couple of springs to limit the operation, or I should say the movement, restrict the movement. Then we have the Fleming's left hand rule to detect the operation. You know that if the index finger is showing the field and the middle finger is showing the current, that the thumb is always going to give you the direction of motion. So accordingly, we are going to use this principle. This is the scale that I just mentioned about. Now if we switch on the power, then it is, of course, I should mention we are talking about the measurement of direct current only, or DC current or voltage. Now when the switch is off, there is no current flowing through the circuit, and therefore there is only a single magnetic field generated by the permanent magnet, but no magnetic effect from the coil. As soon as the current electricity is switched on, then current starts flowing through the electric coil, and because of that it creates a magnetic field of its own, and that magnetic field has an interaction with the permanent magnetic field which is already there, and the interaction between these two leads to a rotation, leads to a formation of a torque, and the moving coil starts to move, which is indicated by the movement of this indicator over this scale. So this is how an electromagnetic meter works. So you can see this is principally a kind of electric meter, or I should say a current meter, which gives you a measure of the current, because with proper design the torque produced because of the interaction of these 2 magnetic fields can be made proportional to the current. And if we want to use this one for measurement of voltage, then we have to do certain additional arrangement, like we shall be seeing shortly. But this is just a picture of the same. Now if we say that I is the current, DC current that is flowing through this, DC refers to direct current, but just as we are talking about current and voltage in both DC and AC sense, so we are going to use the term DC current, though it does not sound good. So let us say I is the current that is flowing through the coil, N is the number of turns of the coil that is there on the spindle in the core, then B is the magnetic field intensity, and L is the length of the magnetic the coil which cuts the length of the electric coil which cuts the magnetic field, also called the active sides. L is the length of that. Then if we combine these two, then the force that is being produced because of this interaction is, from the simple knowledge of electromagnetism, is NBI into L, and that will lead to the formation of a torque. Let us say the torque is Ti, the corresponding torque will be F into D, that is N B D I L, where D is just the width of the coil that we are talking about. Quite often this D and L is also combined together to indicate the total cross section area, total volume of the coil that we are going to use. So, this Ti is the mechanical torque that is exerted on the coil because of the interaction between two magnetic fields. Now, as the coil rotates around its own axis, there are couple of springs. Let us say the spring is having a spring constant of Ks that produce the springs provide a restraining torque. So, the corresponding restraining torque Ts can be given as Ks into delta if delta is the movement or the angle over which the coil has rotated. The springs are trying to restrict the motion or restrict the rotation of these coils, and delta is the amount of rotation. So, the corresponding restraining torque will be Ts. The pointer will reach a balance situation only when these two torques are equal to each other, that is when Ti equal to Ts, that is NBDIL is equal to Ks into delta. Quite often this Ti we write as Ki into I, because if you see everything else where this Ki is equal to N, B, D, L, here all are constants. N is the number of turns, D and L refers to the dimension of the coil, B is the magnetic field, and as we are talking about a permanent magnet, that is also fixed. So, we can write this delta is equal to Ki upon Ks into I, that is directly proportional to the current that is happening or that is flowing through this coil. And now, if the length of this particular pointer is h, then for small angle of rotation we can also write that the displacement experienced by this pointer, the displacement of the pointer lambda will be equal to h into delta, of course when this angle delta is small, or in a way we can write lambda is equal to Ki Ks h into I. So, h again being a constant, that means this lambda is proportional to the current that is flowing through it. So, this is a, that is what I mentioned, it is a current meter, because the deflection of the pointer or displacement of the pointer is directly proportional to the current, and generally this constant that is specified from the manufacturer, because everything else are known a priori, and accordingly just from the knowledge of the pointer movement we can get a measure of the current for this. There are several ways we can make use of the same meter, like we can use as a current meter to measure either voltage or current, voltmeter or ammeter. We can also use it to as a multimeter. Multimeter means which provides you multiple measurements simultaneously by small alteration in the internal circuit, which can give you volt, ohm or milliammeter, that is voltage, resistance or current simultaneously, or just simple ohm meters. We can also have meter systems preceded by amplification. These all kinds of designs are possible with just addition or removal of other electrical components in series and parallel with this particular instrument. However, there are a few losses that can often creep in the analysis that we have shown, like there can be hysteresis effect, there can be repeatability related issues, mechanical friction of the pointer as it is moving over the scale, pointer bearing movement itself can have its own issues. I should means here I refer to the bearing of the pointer, that is where the pointer is connected, that bearing can lead to lots of frictions, and also there may be linearity errors with the spring, particularly after sustained use over a long period of time. Still, this is the most convenient, easy and also accurate way of measuring any kind of electrical quantity, voltage or current, and that is why we use it as both voltmeters or ammeters, particularly when measuring DC quantities. When we want to measure voltmeter, then the meter is connected across in the parallel to the location where you want to have the measurement, whereas in case of ammeter it is connected in series with a shunt resistor. So, if we talk about the voltmeter, let us say the meter resistance itself is Rm and the current flowing through this circuit is I, then if that across the terminal, that is the voltage that is available across this terminal is V, then we can easily write V is equal to I into Rm plus Rv. This Rv is often referred to as series multiplying resistor. So, therefore, Rv is equal to V upon I minus Rm. So, this Rm should be very high, that is the resistance of the meter should be high, so that we can avoid any significant current flowing through the meter itself. Whereas, when we go to the case of ammeters, following the same principle, if I is the current flowing through the primary circuit and Im is the one that is flowing through the meter, then applying the equality of voltage drop between this and this terminal, we can write that Im Rm, that is the potential drop across the meter, should be equal to the current flowing through the shunt resistor, that is I minus Im into Ra, which gives you Ra is equal to Im divided by I minus Im into Rm. So, this way we can easily calculate the resistance required either for the voltmeter or ammeter. For voltmeter, we generally want this meter resistance to be as high as possible to restrict the movement through this movement, restrict the amount of current that is flowing through this voltmeter. Whereas, in case of ammeters, we generally want the meter resistance, or I should say the meter resistance plus the shunt resistance combination to be as low as possible, so that there is hardly any voltage drop while flowing through this. This same thing can be extended in case of AC meters as well. Like in case of AC meters, say for DC, the total power dissipated while current flows through a resistor can be written in two ways. One can be I square R, where R is the resistor, I is the corresponding current, or if E is the voltage drop according or across this, then it can also be written as E square R. Now, when you are writing the same thing, this is for DC, writing the same thing for AC, then the current actually changes with time. So, we can write this one as integral 0 to t I square R dt, where t is the time period and I is the profile of the current that we are considering, or we can also write it in terms of voltage as E square upon R dt, where again t refers to the same time period. Depending on which one is known to us, either the current profile or voltage profile, we can make use of any one of them. Quite often we can also write this one as something like 2 pi integral 0 to 2 pi I square R d omega t. Similarly, this one can also be written as 1 upon 2 pi integral 0 to 2 pi and E square upon R d omega t. So, if we combine both the forms with the corresponding DC form, then what we can write? So, I RMS square will be equal to then 1 upon t integral 0 to t I square dt, that is 1 upon 2 pi integral 0 to 2 pi I square of d omega t. If we assume a common form, like quite commonly you will find that this small I or is given as some reference value I naught into cos of 2 pi small t by capital T, where capital T is the time period, that is I naught cos of omega t. Then correspondingly I RMS square will be equal to 1 by 2 pi integral 0 to 2 pi I naught square cos square omega t d of omega t, and if we solve this, I RMS will become equal to E naught divided by root 2, that is roughly 0.707 I naught. And the same way solving this, we can also get E RMS is equal to E naught by root 2, if of course E RMS, or I should say small e, follows a profile similar to this. that is when small e is equal to E naught cos of omega t. In that case it is also become 0.707 E naught. That is the RMS value will be only about 71% of the peak value, and we can using the AC meter, using following the principle for any DC power measurement, we can get the value of the RMS or peak current following this simple relation. So, this way we generally use any kind of voltage or current measuring meters in using the principle of D'Arsonval movement. Another very important part of any such kind of electrical circuit is the measurement of impedance. Impedance refers to resistance, inductance or capacitance depending on which kind of circuit you are dealing with. If you are dealing in the pure resistive circuit, then the most common way of measuring resistance is in terms of Wheatstone bridge. Any kind, there are several other bridge circuit also, but this is the simplest one and the most popular and most accurate one. That is why we generally prefer going by this. Look at in the Wheatstone bridge what we have. Here we generally have 4 resistors connected in a form just what shown here. So, whenever there is a under balance situation, this V out is equal to 0, and if we connect this terminal C and D through some suitable voltage measuring meter, then we are going to get 0 reading from there. And now if any of the resistance changes, then the value of Vc and Vd will not be equal to each other, and that can be sensed again using a voltage measuring instrument. Actually Wheatstone bridge can operate in 2 ways, like several other measuring instruments, in deflection mode or null mode. Deflection mode means whenever there is a change in any of the resistor, let us say a particular situation there is a small change in the value of R1. So, if there is a change in the value of R1, then there will be some value in this of V out also, it will not remain equal to 0, and accordingly there will be certain kind of deflection sensed by the voltmeter that you are putting there. That is the deflection mode measurement. The other one, the null mode, is whenever we are seeing the deflection, then we are going to alter the value of any other resistor, say R3. So, because of the change in R1 there is some deflection there. If the deflection is over certain scale, we can directly get the voltage measurement, but if the deflection is not over any scale, then we are going to modify any other resistance like R3. We keep on modifying R3 till the deflection goes back to its initial null situation, initial 0 situation. That is the null mode of measurement. The deflection mode of measurement is very easy, because very easy if you are looking for a dynamic measurement, but the problem is in case of deflection mode, the value of the resistance or value of the voltage generated, that is Vc minus Vd, that is a function of this Vs. Whereas in case if there is a change in the value of Vs, we have to recalibrate the voltmeter accordingly. However, if we are going for a null mode, then the final reading is 0, and therefore we do not have to depend on the value of Vs, just we have to sense the change in this value of R3. That will give you a measurement about the change in R1. Several measuring tools like the strain gauges, which we are going to talk about in the next week. There are several temperature sensing devices, etc., which makes use of Wheatstone bridges and gets the actual output signal converted to certain kind of electrical signal through this. Now, how to calculate the relation for a balanced bridge, or to be more specific, the relation between these resistances. As shown here, I1 is the current that is flowing through. Presently we considering this terminal to be open, that is C and D are not connected with each other. So, I1 is a current that is flowing through resistor R1 and R2, and I2 is flowing through between R3 and R4. As the voltage difference between point A and point B is equal to this Vs only, therefore we can write I1 should be equal to this Vs divided by R1 plus R2. Similarly, I2 should be equal to corresponding voltage Vs divided by net resistor in the circuit, that is R3 plus R4. Now, if suppose VCA refers to the voltage drop or voltage rise when you are moving from C to A, how much will be that? That voltage rise should be equal to I1 R1, that is R1 upon R1 plus R2 into Vs. Similarly, VDA, that is voltage rise when you are moving from D to A, that should be equal to I2 R3, that is R3 divided by R3 plus R4 into Vs. So, VCD, net voltage difference when your voltage change when you are moving from C to D, that should be equal to VCA plus VAD, that is VCA minus VDA, that is equal to R1 upon R1 plus R2 minus R3 upon R3 plus R4 whole into Vs. Now, under balanced situation we know that VCD is equal to 0. So, what we can write for this, R1 by R1 plus R2 is equal to R3 by R3 plus R4. So, if we apply suitable modifying principles on this, then we can always convert this particular principle, suitable mathematical operations. This will become R1 upon R2 is equal to R3 upon R4, or generally it is written this way, that is R1 R4 is equal to let me write with some more space, R1 R4 is equal to R2 R3. Look at R1 and R4 are opposite to each other. This is R1, this is R4, whereas R2 and R3 are opposite to each other. So, the products of the opposite resistances will be equal to each other to have the balanced condition. And what about the sensitivity of this bridge? So, we know that VCD is given by this relation. Therefore, the sensitivity will be governed by change in any one of them, that is whenever there is a change in the value of any one of the resistances, there will be change in the value of VCD also. Let us say all the resistances are changing by small amount, like R1 is changing by delta R1, that is to become R1 plus delta R1, this becomes R3 plus delta R3, this becomes R2 plus delta R2, and this becomes R4 plus delta R4. Then delta VCD, remember VCD plus delta VCD, that is a modified value of VCD, but actually should not consider this because this is initially equal to 0. It should be equal to del VCD, dou VCD dou R1 to delta R1 plus dou VCD dou R2 delta R2 plus dou VCD dou R3 delta R3 plus dou VCD dou R4 delta R4. So, this way you can now put the values, like this is simple differentiation, like I can show you one example. So, dou VCD dou R1 will be what? This will be equal to R1 plus R2 into 1 minus R1 divided by R1 plus R2 whole square into Vs is equal to R2 Vs by R1 plus R2 whole square. This way you can calculate the other 4 components and get an expression for the sensitivity. Commonly we do not have simultaneous change in all the 4 resistances. In devices like strain gauges etc., we generally have only one of the resistance acting as the gauge and other 3 remaining constant. So, suppose in a particular situation R1 is the one that is actually your sensor. So, the resistance of R1 will keep on changing and the remaining 3 will remain constant. So, you have to consider only the sensitivity with respect to one of the terms. This is just the way several devices like strain gauge, which is used for measurement of deflection or measurement of strain, resistance thermometers, which is used for measurement of temperatures, they all work following this kind of Wheatstone bridge. But this analysis was done considering an open circuit. Whenever we are connecting or we are closing this circuit using some voltmeter, then there will be certain effect on this. And then what will be the effect on this? Now, instead of having this VCD as an open, we have connected one voltmeter here, which is having a resistor Rm. Then how can we see this as the effect of this Rm? Generally using the Thevenin's principle, there we have to modify this circuit. So, to modify this circuit, just look at these ABCD points. There we can generally draw this one. So, this is your point C, this is your point B, and this is your resistor R1 and R2, these are resistor R3 and R4. So, this is a modified version of the same circuit. Then you can modify this one as a is just a straight line kind of structure. So, you can have basically reduce this one to two resistors. This is your point A and B superimposed on each other. So, this is the point A or B, this is D, this is C. So, what will be this resistance? You have R1 and R2 parallel to each other. So, this one will be R1 R2 divided by R1 plus R2. Similarly, the other one is a combination of R3 and R4 in parallel. So, it is R3 R4 divided by R3 plus R4. And this particular circuit now can be viewed just as one combined resistance between this point C and D, which is R equivalent. So, what will be your R equivalent? R equivalent will be these two resistors in series, that is R1 R2 by R1 plus R2 plus R3 R4 by R3 plus R4. And now, when we have the meter in series, it effectively reduces to a circuit somewhat like this. This is your equivalent resistor and this is the meter resistor. So, your R equivalent, this is Rm and this is your VCD. This way we can reduce the same circuit when you are having this Rm coming into picture. So, what is the net current? If Im is the net current that is flowing through this circuit, then or flowing through the meter I should say, then Im can be, when there was no meter was not present, there was no current flowing through this line CD. Now, as the Rm comes into picture, so there will be a current flowing through this. So, this Im will be equal to this VCD divided by the net resistance of this circuit, which is R equivalent plus Rm, and the expression for VCD was developed in the previous slide, which was R1 by R1 plus R2 minus R3 upon R3 plus R4 into Vs divided by Rm plus R equivalent, which is R1 R2 by R1 plus R2 plus R3 R4 by R3 plus R4. While VCD is supposed to be the actual voltage that you are trying to measure, but because of the presence of this Rm, this resistance Rm, then there will be certain change in this. Means what I am trying to say, that the voltage that you are trying to measure is VCD, and so across your meter there the actual voltage drop should be equal to VCD, but practically because of the presence of this R equivalent Rm combination, the actual voltage drop that is happening across this resistor, let us say, is VCL or VACL, which refers to actual. So, what will be your VACL? Actual voltage drop across the meter will be Im into Rm. So, whatever expression you have, you can convert this to a much simpler form as for doing some manipulation. But generally, we are more interested to know the relation between this actually measured voltage because of the presence of the meter resistance and the true one VCD, which we are trying to measure. So, if we measure this VACL by VCD, then what we have? Your VCL is Im Rm by VCD, and Im upon VCD was Rm divided by R equivalent plus Rm, or if we write this way, it is 1 by 1 plus R equivalent upon Rm. That is, your meter resistance is actually dependent on the ratio of these two resistance, R equivalent and Rm. In a situation, if your Rm tends to infinity, then you have the denominator reduces to 1, that is your actual measured voltage ACL is equal to VCD. So, whatever you are going to measure using your voltmeter, that is a true value, but practical cases Rm is always having some finite value. It is never possible to have a voltmeter with infinite resistances. So, we have to reduce the value of Rm to certain limit, and that depends upon this particular ratio of R equivalent to Rm. Let us assume, suppose a situation you have where this is equal to 10, then your voltage ratio VACL by VCD is equal to 1 by 1.1, which is roughly equal to 0.91. That is, there will be about 1% loss in the 9% loss in the final value. What output your voltmeter is going to show, that will be only 91% of the true output. Therefore, we always have to go for a value of Rm which is sufficiently high. Particularly if we have some idea about the equivalent resistance of this Wheatstone bridge, then we have to choose the voltmeter such that this Rm is significantly high to get a proper reading from this. So, this is the way we can analyze any Wheatstone bridge circuit. This kind of analysis for Wheatstone bridge circuit will repeatedly come back, particularly the sensitivity related issue we shall be discussing repeatedly in case of strain gauge and other devices. But let us move to now AC resistance bridges or AC impedance bridges. AC bridges or AC impedance meters are required when we are looking to measure the value of some capacitance or inductance. Like this is the first example, which is Wien bridge. Wien bridge is a meter which is generally used to measure the capacitance and resistance of certain capacitor. Let us say for this particular case, our objective may be to measure the value of this C1 or the resistor R1. So, just look at this, this is just like a Wheatstone bridge circuit only, but there with a change. Here R2 and R4 two resistors are okay, but this is the one that we are trying to measure, which is a capacitor having a capacitance C1 and resistance R1, and here we have another resistance, a resistor, a rheostat kind of thing, where we can modify the value of the resistance R3 with C3 capacitance in parallel. Whenever we are going for this kind of circuit, we just alter the Wheatstone bridge relation slightly. Let us say this is our arm 1, this is 2, this is 3, this is 4. Like in case of Wheatstone bridge, we have seen that the product of resistances in the opposite arms are equal to each other. Similarly, here instead of resistance, we write the generalized relation in terms of impedance, which is Z1 Z4 is equal to Z2 Z3, Z refers to the impedance of the corresponding arm. Now, here Z2 is equal to R2 because there is only one resistor there. Similarly, Z4 is equal to R4, again there is only one resistor here. Now, what about the other two arms? For the arm Z1, we are having a resistance and a capacitance in series. So, its impedance can be written as R1 plus R1 minus J by omega C1, which is a standard way of writing this. I hope you know this from your basic electrical knowledge. You can review any basic electrical books for this, where J refers to root over minus 1 and omega is the angular frequency of the AC voltage that we are imposing on this. That is a characteristic of this particular AC source. And what about 3 then? Instead of Z3, we generally write Y3, the admittance, which is just opposite of Z3, which is easier to write. It will be equal to 1 upon R3 plus J omega C3. It is easier to write. So, with this principle, now we know that we have Z1 Z4 equal to Z2 Z3, or we modify this as Z2 is equal to Z1 Z4 Y3. So, putting the values, Z2 is equal to R2 is equal to Z1, that is R1 minus J upon omega C1 into Z4 is R4 and Y3 is 1 upon R3 plus j omega C3, that is R2 upon R4 is equal to, if we simplify this or take a product of this, it is R1 upon R3 plus C3 upon C1 minus j into 1 upon omega R3 C1 minus omega R1 C3. So, if we compare the right hand side and left hand side, or I should say the real and imaginary parts of the right hand and left hand side, comparing the real part, we have R2 upon R4 from the left hand side is equal to R1 upon R3 plus C3 upon C1 from the right hand side, that is giving relation between the resistance and the capacitance that we are putting. Similarly, equating the imaginary part, from the left hand side we have 1 upon omega R3 C1 minus omega R1 C3 is equal to 0, because there is no imaginary part on the left hand side. So, 1 upon omega R3 C1 is equal to omega R1 C3, that is omega is equal to 1 upon root over R1 R3 C1 C3. And sometimes we would like to represent omega in terms of frequency, that is equal to 2 pi f. So, your f becomes 1 upon 2 pi into R1 R3 C1 C3 whole to the power minus half. So, this is the frequency of the applied voltage signal that we have got. If we know the applied value of the f, then using this relation and this relation we can calculate the value of R1 and C1. It is possible to write them as exclusive relation between R1 and C1, like from this relation maybe we can get a relation between R1 equal to something and put that back in the second relation to get something, some value of C1 in terms of f, but generally that is not required for our analysis. This is the way we generally analyze an Wein bridge oscillator. Quite commonly we generally go for R1 equal to R3 equal to R and C1 equal to C3 is equal to C, particularly when you are looking to measure the value of the frequency and we have a control on this resistance and capacitance R1 and C1. In that case, what we have? We have R2 upon R4 is equal to 2 and the value of f is equal to 1 by 2 pi R into C. So, the value of the frequency can easily be measured in this particular case for an unknown AC signal. This is Wein bridge is used to measure both resistance and capacitance or sometimes the frequency of an AC wave. Another variation of this, which is called the shading Wein bridge, just look at this, quite similar, but here you have just one bridge or one arm with a plain resistor. This arm is having only a single capacitor, this is having resistor and capacitor in series, and this is having them in parallel. So, if we follow the same principle for all of them, now here we can write following the index given Z1 Z3 is equal to, let us say Z2 R2, here Z2 refers to this particular one. So, your Z2 will be equal to minus j upon omega C2, Z3 resistance and capacitance in series. So, it will be R3 minus j upon omega C3, and for the arm number 1 we are writing the admittance as they are in parallel like we did in the previous case. So, Y1 will be equal to 1 upon R1 plus j omega C1. So, if we put all of them together, then writing Z3 is equal to Z2 R2 Y1, we have R3 minus j upon omega C3 is equal to omega C2 into R2 sorry, this should have been R2, and y1 is 1 upon R1 plus j omega C1. Writing this, combining all of them, we have, so minus j upon omega R1 C2 minus, or I should say plus, we have C1 upon C2. Again we can just compare the real and imaginary part of both sides. Comparing the real part, we have R3 is equal to R2 into C1 upon C2. In this case, commonly our objective is to identify these values R3 and C3, because we generally have control over these three arms. So we can write this one as, so this gives you an expression for the R3 which we are looking for. Similarly, if we equate the imaginary side, then minus 1 upon omega C3 is equal to minus R2 upon omega R1 C2, which gives us C3 equal to R1 by R2 into C2. A very straightforward simple relation once we attain the balance situation, so that this particular relation is valid. You have to remember this particular relation is valid only under balance situation. So once we have the balance, then just from the knowledge of the other resistors, we can get the value of both R3 and C3 to get a value of this capacitance. Quite often this particular circuit is also used to measure the rate of dissipation of a capacitor. Rate of dissipation is given as just the ratio of the resistance and capacitance. Like in this case, it will be just equal to R3 upon C3. You can easily get that from this relation as well. Hay bridge, another very common AC impedance meter or AC impedance meter, where we have an inductance into picture, and our objective is to measure this inductance Lx. So following the same principle, but in taking the inductance into consideration, it is interesting that here we have one variable resistor here and one variable resistor and capacitor here, which can be adjusted, and our objective is to measure this Lx and Rx. So following the same principle, we write Z1 Zx is equal to R2 R3. Now Z1, we as we have resistance and capacitance, we are writing as R1 minus j upon omega C1, and Zx, now it is not capacitance, it is an inductance into picture. So how we should write it? I hope you remember you know this. It is Rx plus, just the opposite way we do for capacitance, it is plus j omega Lx, which is the opposite to the capacitance. Capacitance and inductance, they are mathematically represented as opposite. So while in case of Z1 we have C1 in the numerator, in the denominator, here Lx is in the numerator. So now we can easily go back to our relation, that is R1 minus j upon omega C1 into Rx plus j omega Lx is equal to R2 R3. So we have R1 Rx plus Lx upon C1 minus j into Rx upon omega C1 minus omega R1 Lx is equal to R2 R3. So equating the real and imaginary part, we have from the real part R1 Rx plus Lx upon C1 is equal to R2 R3. Problem is that, like in case of Wayne bridge, we had the similar situation, both Rx and Lx are involved. So what we commonly do is we separate out Rx from this relation, so that we have Rx is equal to okay, let us stay with this, let us do in a different way, let us equate the imaginary part. So from the imaginary part, we have Rx by omega C1 minus omega R1 Lx is equal to 0. So if you take from there, Rx upon omega C1 is equal to omega R1 Lx, that is omega square is equal to, okay, instead of taking omega out, let us take Rx out from this. So, your Rx will be equal to omega square R1 C1 Lx, and let us put it back in this particular equation. So, here we are going to have R1 into omega square into R1 C1 Lx plus Lx upon C1 is equal to R2 R3. Taking Lx out from this, we have R2 R3 C1, and in the denominator we have 1 plus omega square R1 square C1 square, and so that is the expression for your Lx. This can be taken back here to get an expression for Rx, thereby providing you a complete idea about the resistance and inductance of the inductor that you are dealing with. A variation of the Hay bridge, or maybe that is an older version, is the Maxwell bridge, where the calculation is even easier. Quite often this is also called the Wayne-Maxwell bridge. Again another circuit where we have just two resistances in this. This is the inductor that is of our concern, and this is a parallel capacitance resistance combination. So, again if we write for this one, we have Z1 Zx is equal to R2 R3. So, Z1 we can write directly now, because they are they are in parallel. So, we should generally write it as the admittance is equal to 1 upon R1 plus j omega C1, whereas Zx is equal to Rx plus j omega Lx. So, if you put it in the original equation, Zx is equal to R1 R3 into Y1, from there Rx plus j omega Lx is equal to R1 R3 into 1 upon R1. It is not R1 R3, sorry, it should be R2 R3. So, R2 R3 within bracket 1 upon R1 plus j omega C1. So, that is Zx, and therefore, expanding Zx we have Rx plus j omega. We can directly equate the real and imaginary part. Equating that, we have Rx is equal to R2 R3 upon R1, whereas Lx is equal to C1 R1 R2 R3 C1. So, quite straightforward calculation for this. From the knowledge of the other three arms, we can get the value of the inductance. This is the way to show the values of show how we can calculate or make use of different bridge circuits in case of both DC and AC circuitry to measure the voltage as well as measure the impedance of circuits. The one problem, despite being the calculation being such easier, one issue with the Maxwell's bridge is that there is a common Q factor that we commonly calculate, which is given as omega Lx by Rx. This generally is used, this Maxwell's bridge is restricted the value of Q less than 10 only, which is a quite restrictive condition. There are, when the situation demands a larger value of Q, we have to go for some other bridge. There the Maxwell-Wayne bridge is not used, despite being a much easier circuitry to deal with. So, that takes us to the end of this lecture. There are several things that we have discussed. Please go through this lecture, lots of mathematics that we have done, but all are simple mathematics. That is a standard pattern in all the calculations. So, if you follow them carefully, you will surely able to master them. In the next lecture, we shall be solving a couple of numerals to start with, where we can make use of these relations. So, today we have started with the discussion on the relevance of data processing and different components that come under this data processing. Then we have discussed about the types of analog indicators, particularly electrical based analog indicators. Then discussed a bit more about electromagnetic meters in using the D'Arsonval principle. from where we came to the discussion of voltmeters and ammeters. Then we talked about DC and AC current meters, and exclusively talked about the DC and AC bridge circuit. Under DC circuit we talked only about the Wheatstone bridge, but under AC circuit we have talked about 4 different circuits, out of which like Wien bridge, which generally is used for measurement of capacitance, whereas we have also discussed about the Hay bridge and Maxwell bridge, which are used for inductance measurement. So that's it for the day. In the next class we shall be taking it forward, discussing a bit about the digital data processing and finish up of this particular chapter. Till then, thanks for your attention.